Hello students, you all are warmly welcome to our YouTube channel Chemistry Teacher. We are going to present you another lesson regarding the very first unit in chemistry, grade 12 chemistry. Students, we are going to talk about the Bohr's atomic model here in this lesson. Students, so far we have looked at the Dalton's atomic theory, discovery of those subatomic particles, what electrons, protons, neutrons, as well as we have talked about the radioactivity. Then we started talking about the atomic structures, models. In their evolutionary stages, we could find it out. Presenting the Planetary Model by J.J. Thomson. It was Planetary Model by Ernest Rutherford. Next one was the Niels Bohr's, its energy shell model. Then what we are having presently is the quantum model. Students, so far we have talked about the Planetary model and the planetary model. So it was like plums in a pudding. You have electrons in a positively charged globe, presented by J.J. Thomson, called the Planetary model. With the shortcomings were there, it's with the experimental data that revealed by Ernest Rutherford, he presented the planetary model next. So showing that you have a nucleus having all the positive charges and the mass within the atom. Then you have electrons orbiting around the nucleus, like planets are orbiting around the sun. But these electrons, when it was asking some questions like whether these electrons are not spotting on the nucleus. So once he could successfully face such a question like, why is that? These electrons in a circular path do not get attracted by the nucleus positiveness of the atom. So he could explain that why it is not having such, using the anti-centrifugal force. Explaining anti-centrifugal force could balance the nuclear attraction. But when it was further asking the question, when a charged particle is moving in a circular path, it could lose energy, then go in a spiral path as to finally spot on the nucleus. This model, this Rutherford planetary model, could not answer that successfully. And some other limitations also were there with that planetary model. Students, there were some incidences as atomic spectrum of hydrogen. We call it emission, absorption, spectra of hydrogen. We'll talk about those spectra later on. So there were such spectral line series. So could not be explained using this model. This model means it was planetary model. Further, when it was studied, those successive ionization energies, it could be found out some patterns like large increments in their successive ionization energy patterns could not be explained using this planetary model. Anyway, we are going to talk about these emission absorption spectra, atomic spectrum of hydrogen, as well as the successive ionization energy patterns. Further, in more details, in our future kind of explanations with this Bohr's atomic model. Okay, so let's first clear the ground. When there are such limitations, to address them, with the purpose of addressing them, it was Niels Bohr presented this theory called the Bohr's theory. Students, this Bohr's theory based on the quantum theory presented by Max Planck and further developed by Albert Einstein. Okay, in our earlier lesson we talked about this quantum theory, saying that when hot matters, they emit energies as radiations through radiations. They would be doing that as discrete energy amounts, as energy packets, as quantas. So it was further Albert Einstein explained that these energies also have a phase as those of particles. There is such particle behavior you could expect within these energies as well. So saying that it is the smallest at that time. It is the smallest particle you get there within atoms or within matters, let's say. Within matters you get smallest particles. Then within energy also you would be having such small amounts, portions, particles. So with that idea, particle in energy, he named it as photon. Then it was photon. Then it is the energy packet of Max Planck's theory. So students, this photon's energy, the energy packet's energy, we earlier found that out, being its energy, the smallest energy that is represented one radiation or that belongs to one type of electromagnetic radiation would be having an energy packet, a smallest energy amount, let's denote it by delta E, would be directly proportional to its frequency. So the constant for this proportionality is we found out at our earlier time lesson. So it was Planck's constant, which took the value of 6.626 into 10 to the power minus 34 joule seconds. So it's we derived this equation, and it's we applied, we used that equation as to find out the energy of a photon or quanta, smallest energy amount, and energy packet that represent various electromagnetic radiations. So seeing that there is a relationship as c is the velocity of electromagnetic radiations, all takes the same. So E 3 into 10 to the power 8 meters per second equals to nu lambda, frequency into the wavelength. So then substituting frequency there, it we found out that c divided by lambda equals frequency. So bringing it here, we derived our second equation there. In our earlier video, we did that. So it's hc divided by lambda. Students, these we talked about in our earlier session. So then we found out, we use these as to calculate various such parameters when you need the energy amount responsible for a quanta or smallest energy amount means energy packet. So we apply the given frequency with the Planck's constant or given wavelength with the velocity of electromagnetic waves is 3 into 10 to the power 8 meters per second. So with the Planck's constant. So found out energy packet's energy. As well as when you know the energy packet's energy, so apply this equation, we found out the frequency, specific frequency or the wavelength. So we did such stuff there. Then it's my approach now is to explain you what is the Bohr's theory, Bohr's model. So before doing that, it's the planetary model failed to answer why is that. When a charged particle moving, they are revolving in a circular path, let's say it's the electron revolving in a circular path, losing its energy, why it is not finally spotting on the nucleus. That problem, that fraction could not be addressed by the planetary model. There was another idea that Einstein presented, that energy also, especially when those energies are emitted through electromagnetic radiations, those energies also are having some smallest portion within them. It's quite like particle character you get there within energy as well. Saying that energy has a phase of particle, he explained that energy that energy, let's denote it by letter E, that energy equals to mc squared bar. If the particle, that energy particle is moving with the velocity c, then taking the square value of that and multiplying that by the mass, you get the energy that responsible or represents the photon there. In another sense, it explains that you could transform mass into energy, energy into mass. That's what we call the Einstein's equation. Then students, it's another scientist named Louis de Broglie. He combined these two equations, saying that the energy of these, that when energy gets emitted as discrete quantities, and when you talk about the particle within energy, or energy also is having particle character, particle energy within energy, then if that energy particle is having this energy, then it's the mass of the particle within energy and it is the velocity of that. So then combining, joining, adjoining those two, it was Louis de Broglie showed something like this. mc squared equals to, using this, it is hc divided by lambda. Then students, it's lambda, finding lambda out, it is equals h over mc. 1 c to c get cancelled off. So mc is the momentum. So it's in other sense, lambda equals time constant divided by momentum, or in other sense, it's time constant divided by mass into velocity. Okay. So then he has shown, Louis de Broglie has shown, energy has particle character as well as particles have, is that energy character? Yeah, it is energy character, but its energies here we talk about is electromagnetic radiation energy. So they are the waves. Particles are having wave character. This is what we call wave particle duality. Okay. So he means Louis de Broglie derived this equation. So you could expect energy property or wave property within matters, as well as its energy. Its energy also would have particle properties. Okay. So students, we are now going to check for this fact whether it's true. Whether it's true is all the particles, they are moving, when they are moving with certain velocities, do they have wave properties? Are they moving as waves? Then, in the other hand, when you have energies as when you have electromagnetic radiations, do they have particle character, particle properties? But what Louis de Broglie has proven or has derived through this equation, he is saying that yes, you have some. Okay. Let us find that out, whether particles are having energy properties, wave properties, and as well as waves means energies are having particle properties. So students, let me give you some particles with certain speeds that they move, and let me find their wavelengths at those times. As well as finally, we'll do the same thing on energy and electromagnetic radiation as well. Okay students, these are some information regarding few objects. So you have golf ball, bullet, car and electron. It's the motor car, right? So then it's their masses in kilograms. So then it's their velocities here. Here we have got some rough velocities that could be with such objects. Then students, I'm going to apply this equation. It's the de Broglie's wavelength equation. I'm going to find out their wavelength and show you that all these objects are having wave properties as well. So let me do that. Students, I'm going to first substitute the information data given for Bohr. So its wavelength would be equal to h. H is the Planck's constant. It takes 6.626 into 10 to the power minus 34 joules second. Then divided by mc. M is the mass of ball in kilograms is 4.5 into 10 to the power minus 2 kilograms. Then students, it's what you get for velocity is 30 meters per second. Then what you get finally, the answer is in meters. So you would say this joule stands for Newton meters. So then Newton is nothing else but kilograms per meters per square second. Kilograms in kilograms meters per square second. So then this kilograms to kilograms going to get cancelled off. So it's you are going to find this 1 of m meters to meters going to get cancelled off. 1 meter would remain there. So finally it would be in the units of meter. Then what's the answer standing for? Students, it's I'm going to use the calculator that we are permitted to use. What's the calculator? Are we permitted to use a calculator? No, actually not. So this is our calculator. This is a log table. I'm going to use the log table to find out the answer standing for that. Students, it's I'm going to first write the log of these two and add them up. So let me do that. It's bar 2 for this. 0 to 45. 0 to 45 would take 6532. It's 6532. Then it is 1 point. It is 0 to 30. It is 4771. Then you add them up. It is 3 here, it is 10 here, it is 13 here, it is 11 here, it is 0 here. Then you take the log of this. It is bar 34 point. It is to the second of 66. You add small 6. So 66. There I have got. It is second, 66 second. It is 8209. Then it is small 6. Small 6 takes 4. It is 8, 2, 1, 3. It has to be 8, 2, not 1, 8, 2, 1, 3. Then it's this, I'm writing again, 0.1303. So students, it's 0. You need to subtract there. So it is 1 remaining still. It is 9. So it is 7 minus 1 is 6. You get this. It is bar 34 here. So you get the wavelength in meters, 10 to the power minus 34. Then 6910 and log of that. So you could find 6910 there. Roughly it's 490. 4.90 is having 6.02. Then it's you need to have another 8. Another 8 you could find at 9. This is the answer in meters you get, standing for wavelength. So let me write it here. The wavelength of that is 4.909 into 10 to the power minus 34. It is I'm giving in meters. Then students, let me do it for the next one. What's the next one? Next one is the bullet. We'll find it out what's the wavelength when a bullet is passing in this speed, velocity. So again, the wavelength I'm finding out. H is the Planck's constant 6.626 into 10 to the power minus 34 joule second. So then down there it is mass. Mass is 5.0 into 10 to the power minus 3. It's just 5 grams. Then it's in kilograms here. Into what's the speed? It is 350 meters per second. So what you get finally, the answer in meters. Students, let's first find it out. The answer standing for this. It is bar 36990 plus it is 2 point. So it is the 0th of 35. Let's find it out. 0th of 35, it is 5441. 5441. So let's add them up because it is the multiplication. So it's 1 here, it is 13 here, it is 14 here, it is 12 here, it is 0 here. So then it's again, I'm going to find it out, the log of that. It is bar 34. Then it is to the second of 66. Second of 66, I'm having it here. It's 66 second. It's 8209. Then to that you need to add small 6. Small 6 is having 4. 8213. It is 8213. Then I'm going to write this again there. It's 0.2431. Going to subtract. It's 2 here. It's 8 here. It's 7 here. It's then 7 minus 2 is 5 here. Again, it's yes. It is the way. It is the way. So then it's you have bar 34 there. Okay, so it's going to be 10 to the power minus 34. This going to be raised to the 10th power, and antilog of that 5782. So 5782 you have there. 5782 is there. It's at 37th 8. 37th 8. Then 52. It's there. 37th 8 is taking 5775. We need 82. It needs another 7. Another 7 you get at 6. Okay, that's what the answer. Let me write it there. It is 3.786 into 10 to the power 1 minus 34. It's minus 34. It's a very small. Here and there, those wavelengths are too small. So students, let's continue that for the other one is the motor car. So let's find it out. What's the wavelength standing for motor car? When motor car is going or traveling in this speed, this velocity, let's say, then whether it's moving in a wave path, let's find it out. So I'm going to now substitute it to the same equation. Lambda equals h over mc. So h is the same, but m is now quite different. Its students going to be 900. Then the c is 25 meters per second. This is 900 kilograms. This is 25 meters per second. Now the answer I'm about to find out, it would be in meters. So finding that out, I need to multiply these in logs, need to add them up. So I'm going to do that. It's 2 point, what's the 0th of 90? If you are going to find that out there, 0th of 90 is 9542. Students, it's 9542. Then what's the 0th of 1 point? 0th of 25. Let's find that out. You have that as 3979. Okay, it's 3979. So let's add them up. 11, it's 12, it's 15, it's 13, then it's 4. Then I'm going to subtract that value here from this. That's constant. So it's 4.3521. When you subtract, it's 2 you have, it's 9 you have, it's 6 you have, it's 4 you have. So it's bar 38 what you get there. So 10 to the power minus 38, 4692. Students, 4692, and log of that, 46 83 I have is 229.4. 2.94, 4683. But what we need is 4692. Another 9 I need, it's there at 6. This is the answer. Students, it's what you get is 2.946 into 10 to the power what? Minus 38. It's a very, very small value. The wavelength you get standing for what? Motor car. Then let's go do it for electron. Let's find whether it's the same standing for electron as well. Let me substitute those values for electron. So it's the upper value is the same. So for electron, its mass is 9.1 into 10 to the power minus 31 kilogram, and the velocity given as 5.9 into 10 to the power 4 meters per second. You are going to find the final answer in meters. So students, I'm going to try it out. So it's bar 31 point 0th of 91. 0th of 91 I'm having here. It's 9590. 9590. Then it's 0. It's 10 to the power 4. Therefore 4 point 0th of 59. Student, 0th of 59 is 7709. 7709. I'm going to add them up. 9, 9, 12. It's 17. It's when you add 5 here, it's you need to subtract. It's 26. Bar 26 is the answer there. So then it's you need to write it here. You need to subtract it. This is the constant value. So it is bar 26 7299. So let's do the subtraction. It's 4 you have, then it's 1 you have, it's 9 you have, it's 0 you have, it's minus 34 minus 26. It is minus 34 minus plus 26. The answer you get is in 10 to the power what? 10 to the power minus 8. 10 to the power minus 8 is the answer. Minus 8. Minus 8. So it is by 10 to the power minus 8 into 0914. Let's find it out. 0914. 0914 is there. 0899 is there at 3rd of 12th. It is 12th third. Then you need another, it's 99. It's another 50 you lack. So you would find it there at 4th roughly. So this is the answer. Then it's 1.234 into 10 to the power minus 8 meters. It's anyway in meters now. So then let's compare those obtained values, calculated values. Students, for these heavy matters means ball, bullet, then motor car, they are having negligible wavelength values. 10 to the power minus 34 minus 38. Those are negligible. They do not, though we theoretically, though we could call that they are having some wave properties as well, but in practice, they are not realistic values. They truly do not behave as energies of waves. Then what about electron? So this is quite realistic value. Hope you would remember the wavelength of electromagnetic radiation, some radiation. So it's 600 nanometers was the wavelength stood for a red colored electromagnetic radiation wave. In our early sum we did. Okay, so here it is in nanometers, it is 12.34. So then anyway, though this does not belong to the visible region, it's quite like you would find this radiation within UV region. So anyway, the point is electron is having a considerable wavelength. So There are 4. Out of these, electron is small enough to have wave properties as well. Now, for small particles only, you could talk about their wave properties, not these macroscopic or big particles. Okay, then students, finally, we are going to find it out the other way. Other way means whether energy, electromagnetic radiations have particle properties. Shall we find that out? So let's take a light beam, light wave. So let's find it out its particle behavior. How would we do that? Let's apply that in the same equation. Now, knowing the what? Knowing the velocity and knowing the wavelength, let's find it out its mass. It's what I'm telling is you would find out the mass as its Planck's constant divided by lambda c. Okay, let's use any electromagnetic radiation as in our last example we did. Red colored wave with 600. Was that red color? I guess it's a yellow colored wave. Okay, whatever. So it's yellow colored wave with 600 nanometers. So students, you have this light wave with the wavelength, it's in nanometers, 600 nanometers. Means in meters, 600 into 10 to the power minus 9 meters. Let's find out its mass. If it is having particle character, particle behavior, the mass of a photon. So it is mass equals h is 6.626 into 10 to the power minus 34. Then its lambda is 6 into 10 to the power minus 7, let's say in meters. Then its velocity is 3 into 10 to the power 8 meters per second. What you get finally is the mass in kilogram. So let's apply, let's use this equation as to find the mass of light particle. If light has particle character, particle behavior. So students, I can straightly do that as taking bar 34 is the Planck's constant value. The log value is there. I have the second of 66 I have one, second I have one, then it's the sixth value takes 4, so it is 8213, so it is 8213. Then it's the multiplication, when you get the product of 6 into 3, it's 18, so 18 makes it 10 to the power minus 6 there. So 10 to the power minus 6 plus 10 to the power plus 8, it is plus 2 you get there. So it is 1.8 means 0th of 18. Students, 0th of 18 is 2553. So let's substitute here 2553. So let's subtract, it's 0, it's 6 here, it's 6 here, it's 5 here, it's point, it's bar 36 here. So the answer going to be 10 to the power minus 36 into, it is the antidote of 5660. Let's find that out. 5660, you get there 5660 is there at the 8th of 36, 8. So to that 36, 8 takes 5658. Another 2 it lacks, so it's second. So this is the mass of a particle of light if you are having sun. So it's this 10 to the power minus 36 kilograms. So even the mass of an electron takes 10 to the power minus 31 or minus 30 around kilograms. This is too small than even an electron. So students, we could say that though you start thinking, considering light or electromagnetic radiation as particles, particle character, those particles are having negligible masses, therefore they do not possess particle character there. Okay, that's what we could find finally out. Okay, then it's finally what we could find out, the spotlight is spotted on electron. Students, then electron is lucky enough to have particle character and wave character at the same time. This is what we call wave-particle duality. It's the wave-particle duality. Only electron is capable of showing wave character as well as particle character at the same time. It's Niels Bohr used this. Niels Bohr used this in his model, presenting a model for atom. He told that around the nucleus within an atom, you have energy shells. You have energy shells, energy model. At that time, there was no such word. They have got already as energy shells. It was for the very first time Niels Bohr presented this idea. It was just a postulation. It was just a concept that using that postulation you could explain. But in physically you can't show that there are such physically you have energy shells. They are around the nucleus within atom. So anyway, we are going to use this idea further. It's the postulation regarding the energy shells. So what Niels Bohr in his theory regarding atom told was, you have nucleus and you have energy shells around the nucleus. At that time, Niels Bohr presented his idea as these energy shells are circular parts. But it's presently we know that they are having three-dimensional spread. So actually, it was Niels Bohr just not focused on this spatial arrangement, but he nicely explained this concept of energy levels there. Students, what he in his theory told was, there are energy levels around the nucleus. So this is one energy level. It is the first quantum level, first energy level. There are some other energy levels as well. Then energies of energy levels would be increasing when it goes away from the nucleus. If you are going to find that out, your second energy level. This is the first energy level, this is the second energy level. Second energy level would be greater in energy than the first energy level. That's what his idea was. Then students, so when it goes away from the nucleus, the energy of an energy level get increased, while the gaps between energy levels get decreased. What's that? So if you are having a difference in energy between them, when you go to the third energy level, it's the gap between second and third levels going to get decreased than this energy. So it could be a smaller energy difference between second and third shells. This is the third shell, let's say third shell. Then when it goes to the fourth shell, it's going to further increase in energy. E4 would be greater in energy than E3, but the energy difference would be smaller than earlier difference there. So this is it. You have energy shells, energy levels around the nucleus. Energies of energy shells are increasing when it is going away from the nucleus, while gaps between consecutive energy levels are decreasing. Then he further said that you have electrons being filled into these energy levels in the increasing order of energies. What that's supposed to mean? Students, when you fill electrons inside these energy levels, according to him, first energy level could be filled with maximally 2 electrons. So you fill with 2 electrons. If you have further electrons, then you fill it in the second shell. So maximally it's 8 electrons. In that way, you could keep filling those energy levels, but it needs to follow the increasing order of energy in energy levels. That means you need to first fill the smallest energy level is the first level. Then the second smallest energy level. Then the next. Then the next. Then the next. So you need to fill them in their increasing order of energies of energy levels. Electrons has to be filled. So those are the least energy electrons. What they supposed to mean? He further said that when you have an electron, they are moving on the same energy level. It's again, when you have an electron moving on the same energy level, the energy of the energy level is a fixed, constant, certain value it takes. Therefore, though it is moving on the same energy level, it's neither releasing nor absorbing energy. It does not release or absorb energy, moving on the same energy level. But an electron on an energy level could do something like this. It could absorb energy as to excite to upper levels. And an electron at upper levels could go back to the lower energy levels, releasing such energies that represents the energy difference between two energy levels. That's what he presented as the Bohr's model. Again, according to Bohr's model, you have these. You have around the nucleus, energy levels you have. Energies of energy levels are increasing when it is going away from the nucleus. The gaps between energy levels are decreasing when it is going away from the nucleus with increase of energy. Electrons are filled inside those energy levels in the increasing order of their energies of energy levels. Then, an electron moving on the same energy level would not be releasing or gaining energy for the reason that energy of an energy level is a fixed constant value. So, an electron on an energy level would excite to upper levels, absorbing energy. At that absorption, they need to absorb exactly the difference that represents the energy gap between two energy levels. So I'm going to show that later on. So in explaining of absorption emission spectra of hydrogen. So then further, an excited electron could further arrive to earlier energy levels, releasing energy. In that case, those who release energy that represents the energy difference, energy gap between those two energy levels. That's what he presented in his model. According to it means Bohr's model, it was those energy levels are filled with electrons as first maximum with 2 electrons. Then second energy level maximum with 8 electrons. Then third, if it is the last energy level, it is maximum with 8 electrons. But if it is not the last energy level, you get maximally being filled with 18 electrons. Again, fourth shell, if it is the last shell, it would be maximally filled with 8 electrons. If it is not the last shell, if it is one before the last shell, it would be maximally with 18 electrons. If it is not even one before the last shell, if it is 2 or more before the last shell, then it is maximum with 32 electrons you would get being filled there in the fourth shell. So in that way, it's Niels Bohr presented his theory. His theory regarding the model of atom is what we call atomic model, Bohr's model. So it was quite successful for the reason it could nicely explain the way how hydrogen's absorption emission spectra evolve, as well as the reason for those large increments in successive ionization energies. Okay, students, I'm going to use Bohr's theory, Bohr's model on explaining hydrogen's absorption emission spectra as well as successive ionization energy patterns in our next lesson. So I hope that you could understand. It's very simple few points I have shown here. You might have got the idea here regarding what's the Bohr's model and what's the particle wave duality of an electron. Based on that only Bohr presented that idea. What is that? Means I showed that electron only is lucky enough to show particle matter or particle energy duality, particle wave duality. What's the importance of proving that? Students, hope you could remember that early argument. It was why is that an electron does not fall on the nucleus losing its energy when it is moving, when it is going in a circular path. This is the answer. An electron itself is a mode of energy. So, is there any point saying talking as losing of energy? Means if electron represents energy itself, it's useless talking of losing of energy when an electron is moving in a circular path. Hope you could got that. Again, the earlier argument was that if this particle electron is moving, a charged particle is moving in a circular path, it could lose energy and finally going in a spiral path would spot on the nucleus. But now the answer is this electron is having particle wave duality. So at the same time it could behave as a particle as well as an energy wave. So therefore if it is an energy, it's no point of now talking about losing of its energy, because electron itself represents the energy. So therefore it's using that idea Niels Bohr presented this model. It's the energy shell model regarding atom. Hope it's very clear to you. Okay students, with the hope as to meet you in our next lesson explaining absorption emission spectra of hydrogen as well as successive ionization energies. We are going to round up here. Okay students, goodbye.